Hello, this is the next video in a series I'm calling Transformations of Random Variables, and we're going to derive the distribution of the sums of random variables with unequal proportions. And so this is a nice video on how discrete transformations work. And so here we're going to let x1 be a binomial random variable n1 p1, x2 is going to be a binomial random variable n2 p2. And then we have y1 is equal to their sum, y2 is their difference, y3 is their difference plus n2. And we want to find the distribution of each of those. And we will treat them one at a time. So we'll find y1 first. And so the probability that of the distribution of y1, or the probability that y cap y equals little y, is this. So then in for y, we replace this transformation. And then what we do is I introduce a trick here. And so if we introduce another variable and then sum over its all possible values, then it doesn't change this original probability. So this is like saying, you know, if we have one die and we want to find the probability of a 5, going from this step to this step is like introducing another variable or another die, but summing over the probability that it's a 1, 2, 3, 4, 5, or 6. So when you roll both die, you're only really looking at that one die because you're summing over all possibilities of the second die. And that's what we're doing here. We're summing over all possible values. So it's essentially we're summing it out, or if it were continuous, it's called integrating it out. And we're only left with this. But the reason that we do this is a joint probability. So it's a probability of this happening and the probability of this happening. And you can rewrite that in terms of conditional probability. So we write it like this. And then this probability, once we know x2, then knowing x1, is a little easier. And so, and plus x2 is a binomial. And here we're, given the condition that x2 is I, so we can plug it in and then subtract it over. And then technically it's still a conditional distribution, but because x1 and x2 are independent, you can break it apart. And that's why we're left with this. Now, we need to find the constraints here. And because originally we go from 0 to 2, and so all of these are legitimate values, but x1 can only take on values between 0 and n1. So if this goes outside that range, then this probability becomes 0, so you can just ignore them. So actually this is correct, and you can stop there. But I think that we need to find some tighter bounds, and that's what we're going to do here. So here we know I has to be between 0 and n2 for this one. And here, y minus I has to be between 0 and n1. That's what we said, because that's this value. So if we add I over here, then we know I has to be less than or equal to y. And if we add I and then subtract n1, then we know I has to be greater than or equal to y minus n1. And so those are our constraints. So we know that I has to be greater than 0, which is this constraint, and greater than this constraint. So it's the maximum. And then here we know it has to be less than n2 and less than y1. So it has to be less than both, so that that's the minimum. So that's it. So this is the distribution of the x1 plus x2 when these are defined that way. Oh, so I do one more step actually. So here, and then since these are binomial probabilities, we can actually write them in their binomial probability way. So this one, you just plug in, you know, since it's in x2, then this is the density for x2, or the distribution function. And then this is the distribution of y1 plugged in, you know, y minus I. And y goes from 0 to n2 plus n1 plus n2. So here, now let's look at this value, and then we know that y2 can take on values between n and minus n2, but let's find the distribution of y2, so which is probably that y equals little y. So again, we introduced that trick where we introduced an x2 variable and summed over all possible, and we transformed it into this conditional distribution. And then since x2 is I, you can plug it in and take it over, and then it becomes x1 and x2, which they're independent, so you can break them apart and it becomes this. Now we need to find the limits of our sum. Here we know it has to be between here, and this value has to be between 0 and n1. So then if you subtract y over, we know y has to be greater than minus y. And then if you subtract the y over this way, we know I has to be less than n1 minus I. So then the sum becomes this. So I goes from 0 to, or the maximum of 0 and minus y to the minimum of n2 and n1 minus y. So then to find the third one, y3, which is this, which is the same thing. We say probability that y is little y, and so we're over y3. So we introduce that trick again where we sum over x2, we change the conditional probability, then x2 we know is I, so we plug it in and then subtract it over, and we get this. And these are two binomial probabilities. And to find the range, you know, this I has to be between 0 and n2, and here y plus I minus n2 has to be between 0 and n1, and so then you can find those bounds again, and you get this, that the I goes from the maximum of 0 and n2 minus y to the minimum of n2 and n2 plus n1 minus y. And that's it. And that's all I have for today. Hopefully you enjoyed it. If you did, please like the video and subscribe so you don't miss the next one. Thanks. Bye.